Microcontroller and Embedded System, Module 2, the last topic, CMSIS, which stands for Cortex Microcontroller Software Interface Standard. The reason why we need this kind of a standard interface, it is a software which was developed by ARM. The reason why they developed this kind of a software where example was, for example, if there was an application which we need to build using ARM, it requires nearly a small, even if it's a small application, wherein LCD you have one of the application in it involved in it. So it requires probably 500 to 1000 lines to come up or develop one simple application or single application. So if that is the case, then it will not benefit the users. The users who are users, the customers who use this ARM IP intellectual property, requires one application to be built in a quicker time, one product to be built in a quicker time. If that is the case, the main thing is the number of instructions present in the application should be lower as much as possible. So to reduce, what ARM they have done is they have come up with a new stuff like CMSIS, which is a software solution which has libraries defined for many peripherals which ARM has especially. So nowadays we literally talk about neural network. In the recent version of CMSIS version 5, you can figure out that neural network library is included in it. So many of the functions like perceptron, if it's the case, or even back neural propagation, BNN architecture, even those can also be developed. And the requirement is even the hardware should be able to drive that software, which means the hardware should also be complex. It should not be kind of a 8-bit controller as such. It should be a 32-bit controller with good performance, with in the sense clock frequency should be higher. One more example which I can address over here is, you think as if you're working in Arduino platform. So Arduino to ARM swap, when you swap from Arduino to ARM, you find it very difficult to understand the program. Since you people, if you're not very good in C or C++, then ARM works in C or C++ environment also, whereas Arduino you do not require really C or C++ basic concepts. So directly by looking at the instruction itself, any user who uses, he will come to know what that instruction is. So simple it is. LCD interface, if you want to do, then basically what you'll do is you'll just include a header file, and when you include a header file, indirectly that program is gonna call lcd.h and lcd.cpp files. So in lcd.cpp file, you'll be writing all the definitions like are you gonna send the command, are you gonna send the data. So the LCD program itself is huge, which has 100 lines of codes. But in the Arduino environment, just with the help of one single library, you can perform many things, many operations like clearing a LCD, clearing first line in the LCD, everything could be done. And the reason why we use this kind of a library is because we don't want to waste the time for doing some application which has already been done. So we can concentrate on our main or core application in that case. So that is where we can include this kind of a library, and we can shorten up the product speed. If you want to develop one application in a short span of time, then you can always try to include as much as possible libraries, and you concentrate on what application you are supposed to design, that you concentrate rather than the basic concepts. Now let's look at did we use this kind of a CMSIS file already? Is it been used, or we have not yet used? Let's look at it. So to explain this, let me go back to a program which is written in embedded C. So hope you are pretty much clear with the part B experiments. In part B experiment, what we do is we use 3 files. System is optional, startup file is essential, we use this. Along with that, we use our .c file. So here your startup file, what basically this has the, I'll open this file. We will have a look at, basically this contains your interrupt request handler. IRQs as well as exceptions. Everything is included in it, and mainly so this program will run, and the job over here in your particular application is to reset your program. If your user program is hanged in between, then literally by using a reset button, as soon as you press reset button, this startup file will be called, and it is going to call back the program, or else it is going to rerun the program from line number 1. That's something like reset the program. So that's why we require this startup.lpc x6 file. And we do have one more file which we call it as system file. Now startup lpc file is your CMSIS file. This is your CMSIS file, and you can figure out what is the version of this CMSIS Cortex M3 for NXP test. So if you are working on some other platform like STM microelectronics related Cortex M3 processor, if you are using, then you cannot afford to use this library. This library is intended to be used in NXP environment, so it is for LPC1X series. And there is one more file which is a system file. Even this is your CMSIS file. I hope you're clear with startup file. If you want to figure out any other functions what this consists of, you can go through. It has all exceptions and interrupts. Its service handler is addressed in it. All whichever is required, you can use it. And the next file is startup. After startup, you have a system file. When you expand the system file has 4 more file which will be called when you are building this project. When you don't build the project, then this will not be expanded. As soon as you build this project, build this application, program 2 in this case, this 4 files will be expanded. And let's look at what this content, what each of this file contains. So first of all, let's look at the system.lpc.c file. So this system.lpc.c file, you can go to line number 409. That is only one program which will be running when you are invoking this file. So this system file implies initialize your system. Initializing the system inside implies over here you are supposed to configure the clock frequency. Your system clock frequency should be addressed. So altogether you have 3 clock frequencies which you can use optional, but literally by default XTAL, this is your main clock frequency, and this clock frequency operates at 12 megahertz, and it is introduced here. And other frequencies, if you want to use real-time clock frequency, it has been addressed as 32K here, and you have internal real-time clock. So this is set for 4 megahertz. So this frequencies are configured here, but you may question me which frequency will be called. So this is the default frequency which will be called, and how it will be called. To call this, there is one mode which you need to enable. So you have a system control status register bus, SCS register you have, and in that you need to set some fields in it. So in the 4th and 5th field, they are used for selecting the mode in the sense range for your frequency. Suppose if you want to operate your controller with a very huge frequency, then you can select one. When you select this bit 4 of your SCS register as 1, then 15 megahertz to 24 megahertz frequency you can set. Suppose if you are using it as 0, 1 megahertz to 20 megahertz frequency you can set. So here we are using 12 megahertz, which is inside this range. So you can set this bit 4 of your SCS register as 0. Similarly, 5th bit is for selecting the or enabling the oscillator frequency. For enabling the oscillator frequency, you are using 5th bit. So in turn, the value of SCS register, which is down the line over here, SCS register value, you can find it, which is set to 20. This is the value of SCS value. So by default, this will be set to 20, and this is how you address it. So by addressing this fact, then automatically the system will be initiated, and the system will be running at a clock frequency of 12 megahertz. That is the job of this .c file. Understand? Configuring the clock. which clock to use, what should be its frequency, how to enable the frequency. Those will be defined in this .c file. So that program is system init. Remember the function system init. Then we have stdint. This is the header file which is used in both. So few instructions I'll explain what basically this contains. So this contains always, probably if you do remember, some of the programs we have used unsigned int, signed int. So if we address signed, then for signed, how many number of bits should be allocated for signed, and what should be its maximum value, what should be its minimum value, all things needs to be defined, and that is defined in this stdint. This defines the class type. For the class type, what should be the minimum value, what should be the maximum value, and what should be the capacity for this. For example, think as if it is signed by default. Signed, if we address, then 8-bit is the total capacity provided to it, and it is character type here. Similarly, short, it is 16, and if it's 32 and 64, you have typed it sign itself. In that, you have 32 and 64-bit. So this is actually your data bits specification, and this will be the notation which you'll be using in the program. Similarly, for unsigned, you define this, and you can figure out below. You can look at for the standards, different classes, what is the minimum value, what is the maximum value. Even this you will be defining in the program named as stdint. So that's what this contains. Along with that, it do contain things like including your C++ library namespace, because if you want to use C or C++, you can use namespace for C++ and external C. So programs, semantics related to C, everything will work. You will be including the compiler. C or C++ compiler has to be introduced here, so to make your program run. Then we have lpc1xx.h. This is your main file. This is your device. This is your device header. We'll talk about device header later. So this has many functions. Basically, this has the exceptions and interrupts. Their priorities are defined in this case. Along with that, that's not the only stuff this has to do. One thing is exception and interrupts. Their priorities are defined. So non-maskable interrupt, its priority is set to lowest, which is -14. Similarly, you have interrupts which are starting from 0. So negative number implies exception. They are given more priority than the interrupts. These are the various interrupts you have, which you will be dealing with. Along with that, this has the functions for pin block, pin connect block. You might have come across. For DAC program, we had used this pin block. Pin cell concept we had used. Pin cell, how many you have, what is its capacity, it is at rest. So pin cell, it can work as it is a GPIO pin. It is an input or output pin, and the capacity is 32-bit. That is what is addressed in this structure. And pin cell 0 to pin cell 10 you have all together. Each capacity 32-bit, and it can be input or output. Similarly, you have pin mode block, which we haven't used so far. Even its capacity, data type, class defined in this. Along with that, you have many peripherals. For example, if you remember PWM program which was done, there we had used many kind of functions like LER registers, MR0 registers. You can find those registers, timer register, MR0 register, MR1 registers related to pulse width, MCR register, MR0, MR1 register. Even this is defined, declared in it. So this has almost all the related components which you want to run an application. Everything is there. Directional flag, FIO pin flag, FIO set flag, FIO clear flag. So what you have to do is you have to include this. Then you can use all the definitions whatever this is having. This library is very much important. That's why we include this at the beginning. Then you have core cm3.header file. So this is your header file, which has simply, you can go down the line, have network vector interrupt. So you have the starting address of almost all the memory map register that will be addressed in this you can figure out the memory address. For example, just go to line number 267. There you have starting address for system control space base E00 E00. We have looked at this region in the while discussing memory map. So this was the starting address for your system control space base. Similarly, you have many other memory mapped registers for handling NVIC, network vector interrupt controller, DWT block, DWT register. All those memory address, starting address, everything will be addressed in this file, core memory file it is. And also some of the functions like you might have come across some functions like PSP, MSP. Using C program also we can read the status of PSP, we can read the status of MSP. So you can use get and set method. Even its definition you can figure out. Here it has been defined, here it has been declared, but it will be defined in the core cm3.c file. In .c file, the implementation of every instruction which you encounter, this is having majority of the instruction which cannot be implemented using normal C program. You can see set MSP, also you can see REVSH. So not all, some of the instructions are defined here. Try mask, fault mask, get function, set function. So you can talk about this file, this CMSIS file, and few components present in that you can highlight. Finally, system.header file. So this is header file, its implementation is written in .c. So system.header file job is as addressed. So it will be calling the function system init, which is defined in system lpc xx.c. So this program, what literally it does is, hope you can figure out. Basically, if your intention is to blink the LED for a while, on the LED of the LED, 8 LEDs assume, then you can use this program. Now here you select this FIO directional flag, port 0 is used, directional flag we will be setting it as FF, implies the least significant 8 bits of the port 0 are set to 1, implies you will be it will be acting as the output port. Then we use while always, while true, LPC GPIO 0, FIO set the first 8 bits of port 0 as 1. So doing that, you're sending this data onto the peripherals. Assume that the connected devices are LED. So in that case, the LED will glow. After a while, introduce a delay. So it will be on for few seconds. Then you can reset all those bits. So you can use same number of bits, you can use FIO clear. So these two commands you can figure out, it will be available in your lpc1xx.h file. Okay, so that is essential. So this is one program which is explained. Suppose if in the in the exam, if it's asked like write a program to blink a LED, hope you can address this program itself. And there is one more program which I'll show you with the help of CMSIS library. Now you have used CMSIS file, but CMSIS libraries are also available in the internet. You can download. If required, I'll provide the link in the description, so you can figure out that. Just check how you can run the same application using CMSIS library. CMSIS library has for each peripherals, its functions are defined. It is not in general for all. Few functions, like for GPIO, I have downloaded CMSIS library package. It was having for GPIO I2C, but I'll demonstrate how GPIO CMSIS library package you can use, and how you can modify this program using that CMSIS library. So let me close this project and open back that project. Open the project with the CMSIS. So in CMSIS, there is only one difference. When you observe the code, the main program is somewhat different, and you have to introduce one header file which is addressed here. So this is the program. LPC1XX, same as we had seen previously, but this is actually the CMSIS library which I was talking about. This header file should be introduced in the main program. And now just observe, this program simplifies your previous program. Here I'm not supposed to use LPC. LPC is already known. Rather than that, this library has all definitions for GPIO. To configure the port as a input or output, you have GPIO set tag. Instead of LPC GPIO to FIO DIR, you can use this program, and this works very in a simplest way. So here, rather than adding a value, you can specifically design like GPIO, it is GPIO, and which port you are using, what is the value to be introduced onto the bits, and what is the status, is it working as an input or is it working as an output. So here, if the port is working as output, directly write 1 here, and if you want 8 bits to be made 1, then you can write FF here, and 0 implies port 0. So this is more neater way to write the program. So this is only possible provided you have CMSIS library for GPIO. How to include this, I'll just tell you. From where to get this CMSIS library, I'll just tell you. If required, you can work on it and just see the difference between this. And also, we will not be using FIO set and FIO clear. Instead, we will be using this command, GPIO set value. Again, remember, LPC is not there here. LPC command you can ignore. So just you have GPIO set value and GPIO clear value. So this makes 0, and this set value 0 FF. So it 0 implies port 0, sorry, port 0, and port 0, this should be the 8 bits you are using, and it all will be made 1. Then again, same bits you make it 0. So set the value, clear the value. So this is a simple program using CMSIS library, and you can figure out here there is one extra file introduced, LPC17XX underscore GPIO.c. This GPIO.c file should be added to your project. Previous program we did not have this. Now this source file for GPIO should be added, and also in the main program you have to include LPCXX GPIO. And one more thing is, you have to the location, the area from where you get this is actually the link URL from where you can get that CMSIS driver, CMSIS library driver. And once you install the program, the program, once you extract the program, it will be the form yeah. After extracting, this is what you get, and you can figure out the header file and .cp file. .c file and header file will be included in this. The source folder is having the .c file which you require. This has other files. Other than GPIO, you can use PWM, you can use ADC CAN, SPC, I2C, all protocol related libraries are also available. You can use this so that the program length could be drastically reduced. Also ensure that you include this .h file. This .h file for all those libraries .c, you have a .h file associated here. This should also be included. So that's about your CMSIS. Hope you understood what this CMSIS is. Now I'll go back to the slide from where we started. So this is the block diagram of your CMSIS. Basically what you have here is you have 3 modes: application, the program without operating system, and you pass it onto the CMSIS files. This acts as a library. It will facilitate, or it will make your program short. So this CMSIS can be connected directly to the hardware environment. So write the program, small program you can write, and this will use many libraries. All the libraries are included in CMSIS, and thereby you can make the communication happen between the software and hardware. So this hardware could be driven with the help of the CMSIS. So this is the user application. Suppose you think as if you have a computer with ARM or processor involved in it. So in that case you require kind of a embedded operating system. This is used for running many applications or services available in your processor. Almost all the load you will be taking now in this case. So if there are some services which cannot be driven with the help of operating system, then you can use separate softwares, not the operating system. Separate softwares could be used to service your utilities, and that you can call it as a middleware. So altogether, so softwares are of this form. This is a user program, your application program. This could be also, this could also be used embedded operating system to make the system look more convenient, reliable for other party to use. Middleware as addressed for those services which cannot be serviced with the help of operating system, that you can provide a software. So that's what you have this slide. And CMSIS have standardization, or almost all is defined. So here you have different layers. Which file it is referred, you can refer as I have addressed. So you can refer the CMSIS file which was just addressed now. Look at the contents present in it, all are addressed here. Okay, so that's what you have today. The time being, a few things you can just take a note of the CMSIS file. This is important. The device file, startup code, what you have, and core CM3 file, CM3H file as addressed, interrupt number, everything, all peripheral related register definition you will be having in this device.h file and device.c file. Other header files we haven't used. init I think have used one more file which had those UINT definition, its mode, everything was defined in it. Have device.h file. This has everything. This is your startup code. So this is your CMSIS file structure. Also you can make a note of this diagram. Same thing as addressed. CMSIS user application. You can have a middleware to drive some of the units present in this hardware. So this hardware, you are supposed to run or trigger this components using some program. So that you'll be using this as an intermediate stuff to drive your hardware. So this is your CMSIS structure. So hope this is useful for you. So that's what you have in module 3. Wind up the session time being.